All right, let's start. Good morning. Okay, let's try that again. Good morning. Good, much better. All right, so the exam results have come back. Your TA should have your exam scores by now, and he or she has been told to enter the scores on WebAssign. So you may see it later today, maybe tomorrow. But if you do not see your score by, let's say, Wednesday, you let me know, and I'll nag your TA a little bit about it. The average, course-wide average, 79.5. It's very high, but it's exam one. Not too much has happened yet. It's a very good average. I'm very happy to see that. So congratulations if you got a good score. But the cutoffs for this exam only, let me write that down. These are the numbers for exam one only. Each exam will use the average and how the scores are distributed to determine the cutoffs for that exam. For this particular exam, we're going to go with 90, 80, 65, 50. If you got 90 or better, consider that an A. If you got 80 or better, consider that a B, and so on. Okay? So once again, if you got a good score, congratulations. Keep up the good work. If you didn't get a score that's as good as you had hoped, it's only one exam. You got two more exams, and you have the final exam, which weighs as much as two exams. Okay? So there's plenty of time to bring your score back up. So there's no reason to panic yet, even if you didn't get a score that you had hoped. You should get your exam booklet back in recitation sometime next week. Not this week, sometime next week. The reason is because there's still people waiting to take the makeup exam. And the makeup exam is different from the regular exam, but I don't want the TAs to return the exams this week and have them go over the exam in class. That may give the people waiting to take a makeup exam some advantage that it's not very fair. So we're going to wait until next week before we return the exams. Okay? So make sure you check WebAssign today, tomorrow, and Wednesday. Be sure you see your exam score. All right. All right, so today we're going to look at section 3.3. We're going to look at the derivatives of trig functions. And you're going to see it's like last time. As long as you know things about sine and cosine, you can do a lot with just those two pieces of information. Let's start with sine. Okay, we're going to find out what the derivative of sine is. So let's start by sketching the graph. Okay, we all know what sine does. Starts at 0, goes up to 1, comes back to 0, goes to minus 1, back to 0, back to 1, and so on. It goes no higher than 1 and no lower than minus 1. It reaches maximum the first time at pi over 2, comes back to 0 at pi, goes to minus 1 at 3 pi over 2, goes back to 0 at 2 pi, and so on. All right, so this is our sine graph. Now we know from the things we've done in the past, as long as we have the graph of the function, we can use that graph to draw the derivative of that function. And that's what we're going to do next. All we need to do is to look at the slope of the tangent lines all over that graph. Okay, so let's see. Tangent line is 0 at pi over 2. So we know f prime is equal to 0 right here. Also right here. Right here again. Here, right? So we know on the graph of f prime, we will get 0 at these locations, at pi over minus pi over 2, at positive pi over 2, at 3 pi over 2, and that would be 5 pi over 2. I also see from going from minus pi over 2 to positive pi over 2, the graph is getting higher and higher. And if you look at the tangent line on this portion right here, this portion is going to have a positive derivative because the tangent lines are all going to have positive slopes. Start at 0, ends at 0, remaining positive the entire time. So we know the graph of f prime is going to look something like this, right? Starts at 0, ends at 0, remaining positive all the time. Similarly, from pi over 2 to 3 pi over 2, starts at 0, ends at 0, but the entire section right here will have negative tangent line slope. Therefore, it's going to have to go below the x-axis. We continue doing this, we'll see this kind of thing. Here, negative slope. And it's going to come back up. Okay, now look at what's going on here. You start at the maximum. You go to 0 at pi over 2. You go to minus 1 at pi. Go to 3 pi over 2. You end up at 0. This looks like a cosine graph, right? Maximum first, 0 at pi over 2, minimum at pi. This is a cosine graph. So we see that the derivative of sine turns out to be cosine of x. And if you do the same thing with starting with cosine and sketch the derivative of cosine, you will see that the derivative of cosine is negative of sine of x. Okay, that's something you probably want to try on your own. Sketch the graph of cosine and see what the derivative looks like. You'll see it looks like the sine, but actually it's flipped upside down. To flip upside down, you just put a minus sign in front of the graph to get your reflection about the x-axis. All right, so knowing these two, we can handle all the other trig functions, sine and cosine. So derivative of sine is cosine, derivative of cosine is negative sine. We can handle the derivatives of all trig functions. For example, if we're looking for the derivative of tangent, as long as you know how that function is related to sine and cosine, in whatever way it is related to it, if you can find out how it's related using what you already know, you can deal with any trig function. For example, for tangent, we know tangent is sine over cosine. So if I know the derivative of sine, I know derivative of cosine, and I have sine over cosine, what I can do here is to use quotient rule and these two to find the derivative of tangent. Quotient rule would take the denominator, low, d high minus high d low all over low squared. All right, so basic quotient rule, and now we got these two things. We already know what they are. Derivative of sine is cosine. Derivative of cosine is minus sine. So let's substitute those in. We'll get cosine times cosine, which is cosine squared. Minus sine times minus sine is plus sine squared. Downstairs is cosine squared. And what's on the top? What's cosine squared plus sine squared? 1. Yeah, absolutely. So this is 1. 1 over cosine squared. Now normally you would see the derivative of tangent written as, the first thing we do is rewrite this as 1 over cosine, whole thing squared. And this we know is secant. So normally you would see the derivative of tangent given as secant squared, even though there's nothing wrong with 1 over cosine squared. Okay, let's do another basic one of the 6 basic ones. Let's do cosecant. Okay, so once again, figure out how this thing is related to sine and or cosine, and then use an appropriate rule to deal with it. How is cosecant related to either of those two? What's cosecant? 1 over sine, right. All right. So again, let me use the quotient rule to proceed from here. We'll get low derivative of the top. Top is a number, a constant. Derivative is 0, right? Low d high minus high d low, d sine. Derivative of sine is cosine all over sine squared. Zero minus cosine over sine squared Okay, again, normally this is fine, absolutely fine. But again, normally we will see this given in a slightly different form. Yeah, negative, sorry. Yep, thank you. And I'll put a negative right here. Thanks. Okay, so I'll borrow one of these factors of sine. Make it 1 over sine, and the rest of it is cosine over sine. What's cosine over sine in terms of one of the 6 basic trig functions? Cotangent, good. So negative cotangent of x. This is cosecant, of course. Okay, so there you get the derivative of cosecant. Now, it's a good idea to know the derivative of the 6 trig functions. And you can get all 6 the same way we just did. The rest of the 6 basic trig functions. And I'll list all of them over here. These are 6 formulas that are good to know. But if you only know just 2, then you want to know sine and cosine. Everything else can be recovered from sine and cosine. Okay, so start with sine. We know that already. That's cosine. We know cosine has a derivative that's negative sine. We found out earlier that the derivative of tangent is secant squared. And doing exactly what we did for tangent, you can find the derivative of cotangent. It turns out to be negative cosecant squared. Derivative of secant turns out to be secant x tangent x. Derivative of cosecant, we did that earlier, is negative cosecant cotangent. Okay, it's great to know these 6 too. If you can memorize these 6, perfect. But as long as you know the top 2, you'll be okay. All the other 4 can be recovered if you need to. But now notice, look at them here. There's a pattern going on. The derivative of tangent is secant squared. The derivative of the co-function of tangent, cotangent, is the same thing, but with the function changed to its co-function. So secant squared shows up for tangent. The co-function of tangent is cotangent. The derivative has the same thing. It's the co-function of that. So if you know the derivative of tangent, you also know the derivative of cotangent. Put a minus sign there, put a co-function there. Same thing here. Secant is secant tangent. The co-function of that, cosecant, has negative cosecant cotangent. So the pattern is actually pretty nice. Also note that the derivative of the co-functions are all negative. Right? The cosine, cotangent, and cosecant. All of these co stuff have negative derivatives. And the derivatives of each one of these is related to its cofunction. Secant tangent, cosecant, cotangent. Again, great idea to know all 6, but at the bare minimum, the top 2. Probably even better to know the 4, top 2 plus the 2 on the left. The other 2 are just following them. You know all 6, even better. Okay, now let's look at more complicated stuff. These 6 basic stuff is not interesting. Let's look at more complicated functions involving trig functions. And there's a very important point I want to make about trig functions. We'll see at the end of this example. Let's take a look at tangent x minus 1 over secant x. The first thing I want to do is to simply apply the rules we saw on the last page and the quotient rule. Yeah, I'll make that, we'll see that at the end. It's a point I want to make. So the first thing, if you just look at it and go, okay, let's use all the rules we saw, and then apply the quotient rule. And let's see what happens. So here's y prime. And let's do low d high derivative of the top. Derivative of tangent is secant squared. Derivative of minus 1 is nothing. Low d high minus high d low. Derivative of secant, last page, secant tangent. All over secant squared. Okay, it looks pretty complicated, but the first point I want to make is that no matter how complicated these trig things may look, there's often a way to vastly simplify them. I'll show you how to do it with this one. Let's distribute things out. We have secant cubed minus, here we have tangent, tangent, secant. So minus tangent squared secant. Minus minus 1 times secant tangent, so plus secant tangent. Downstairs, secant squared. Okay, upstairs still looks awfully complicated. But if you look through here, we see a common factor of secant. Let's take that out. First one will be secant squared. Then minus tangent squared. Here is a plus tangent. Okay? Still looks pretty messy, but we can see that we can take one of these secant out with one of these secant downstairs. What else can we do? Anybody recognize what this is equal to? 1, yeah. Okay, this comes from the Pythagorean identities. So this is 1. So let me list the Pythagorean identities here. All right, we know that, right? If you divide through by cosine squared, divide everything by cosine squared. Cosine squared over cosine squared is 1. Sine squared over cosine squared is tangent squared. And 1 over cosine squared is secant squared. So that's where this thing came from. If you move the tangent over to the right, secant squared minus tangent squared, that's where the 1 came from. If you divide this by sine squared through, then you get cosine squared over sine squared, that's cotangent squared. Dividing by sine squared, this is a 1. And 1 over sine squared is cosecant squared. Okay, so again, knowing the relationship between cosine and sine, just by dividing cosine and sine through, you get the other two. There's no need to memorize the other two. Just know the top one, and you can recover that as needed. Okay, so anyway, what else is left here? We have 1 plus tangent over secant. And this can be simplified further. Tangent is sine over cosine. Secant is 1 over cosine. And 1 over secant, by definition, is cosine. And here, if you multiply top and bottom by cosine, you get sine. Okay, so at the end of the day, it turns out to be a pretty simple derivative, cosine plus sine. Okay, we did have to do quite a bit of work to get to here, but we got there nonetheless. Now look at the last thing we did over here. We changed everything back to cosine and sine after we got the derivative. So perhaps a better thing to do, actually it is a better thing to do, is maybe to start doing that before we take the derivative. Change all of these to cosine and sines, and then deal with the derivative. And let's see what happens. And we'll see what if okay, so let's see what happens. Upstairs, tangent is sine over cosine. And that 1, let's write 1 as cosine over cosine. Well, actually, no, let's not do that. There's an even better way. Let's do it this way. Let's just divide everything through by secant. Tangent over secant, simple. Minus 1 over secant. That's better. Remember, you can divide everything by a common thing as long as there's only one of that thing in the denominator. If this thing were flipped upside down, you cannot divide it by tangent of -1. So this, we saw it earlier, but let's do it again. This is sine over cosine over 1 over cosine minus, by definition, cosine. That's a sine. That's a cosine. Okay, and we haven't changed the function at all. We simply rewrote it using definitions of trig functions. And what we got here is a vastly simpler function than the one we started with. They are identical. Their derivatives will be exactly the same. But this is a much better form than that. That requires quotient rule and a bunch of manipulation. This, just two simple trig rules. Derivative of sine is cosine. Derivative of cosine is minus sine. Right? And then we get cosine plus sine, which is precisely what we got, but we got this a lot faster. So the point here is always consider rewriting or simplifying trig expressions first. It's kind of like knowing the quotient and product rule. Sometimes you don't have to use them, and sometimes it's not a good idea to use them. Even though it's always okay to use them, as long as you got the right form, it may not always be the easiest way to handle them. And here is a perfect example. Let's look at one more. Cosecant over 1 plus cosecant. Okay, remember, if downstairs has multiple things added to or subtracted from each other, you cannot divide them individually. So this is not equal to cosecant over 1 plus cosecant over cosecant. Okay, you cannot do that. You can only divide through if the denominator is one thing. Okay, so we can't do that to simplify, but we can still change everything back to sines and cosines. If we get lucky, we'll see what we got on the last example, something very simple. But even if we don't get lucky like that, handling sines and cosines is still easier than handling the other four. The derivatives are much, much simpler than the other four. So it's always a good idea to try that. At least consider doing that. Okay, downstairs, upstairs is 1 over sine, of course. Downstairs is 1 plus 1 over sine. I have a complex fraction here. Let's multiply by sine over sine. We can always multiply by 1. So we have a 1. Downstairs is sine times that whole thing. So sine times 1 is sine. Sine times 1 over sine is 1 plus 1. Okay, so we weren't able to get rid of the fraction. It's still a fraction. But at least we simplified this by quite a bit. First of all, the numerator is no longer a complicated trig function. It's just a 1. And downstairs we have sine and 1. Sine has a very simple derivative. Cosecant has a slightly more complicated one. Question? You can't do that, but you can, but then that requires another rule that we haven't seen yet to take the derivative of. We'll eventually encounter that rule. Actually, pretty soon we'll encounter that rule to handle that kind of situation. But for now, without knowing that rule, we have to use quotient rule. All right, so I'm going to start by using the quotient rule here and then the basic trig derivatives. Here's low. Now the advantage of having numerator being a 1 is that d high is simple, 0. Derivative of 1 is 0. Minus high, derivative of low is cosine, simple. All over denominator squared. Okay, so minus cosine over this thing. There's almost never any reason to multiply this out. Generally, there's not going to be a way to simplify further. Just leave it as is, and then that would be good enough. Okay, so we still have to use quotient rule, but we only had to use one basic trig derivative, sine. That one is easy to remember. Cosecant is a little bit more complicated. Okay, so remember, seeing trig stuff, consider rewriting, consider changing things to sines and cosine, and simplifying some way before you jump into derivative. But it's always okay to simply use all the trigs, derivatives, and the rules you know. You just may have to handle more complicated stuff. Now we're going to look at two special trig limits. The first one I want to look at is the limit as theta approaches 0 of sine of theta over theta. Now we know that sine of 0 is 0, and theta goes to 0 is also 0. So this goes to 0 over 0. That, we all know by now, means that there's more stuff going on. The limit cannot be found that directly, and there's something behind this that we had to figure out. The first way we'll figure this out is to make a table. Back to the basic way to figure out these limits. We'll choose a few values of theta, find out sine of theta over theta. And I'm going to choose minus 0.01 for that, minus 0.001, 0.001, and 0.01. We just choose theta values close to 0 and then squeeze towards 0. By the way, how should those values be measured? In what way of angle measurement? Radians, very good. Remember in calculus, Always use radians. Derivative of sine is equal to cosine is only true if you're measuring that x in radians. It is not true if you're measuring that x in degrees. Always in radians. No exceptions. If you're given degrees, change it to radians before you do anything else. If you plug this into sine of that over that, we get 0.49 and an 8. 2, 3, 4, 8. And then this one will give me 1, 2, 3, 4, 5, 6 9s and an 8. 1, 2, 3, 4, 5, 6, and an 8. This one is mirroring that. 6 9s and an 8. That one mirrors that. 4 9s and 8. And actually going to 0 when the angle is so small, the difference between radians and degrees is very tiny. So actually, even if you had used degrees, it would be okay, but for the wrong reason. You should still stick everything into radians. So looking at this right here, it appears that the more zeros I add in front of that 1, I'm going to get a longer string of 9s, with this 8 being pushed further down. So this appears to suggest that the limit as theta goes to 0 of sine of theta over theta is equal to 1. Okay, there's another way to see this is true. If you sketch a unit circle, just a quarter of that actually, a unit circle has radius of 1, right? If I make a triangle in here, this distance right here is a 1. If I put theta over here, then we know sine of theta is opposite over hypotenuse. So sine of theta must be this over 1. Therefore, this side right here must be sine of theta. And cosine of theta is adjacent over hypotenuse. So the adjacent side is cosine of theta. Okay, now look at this segment right here. We know the formula for a circular arc is S is equal to radius times theta. If radius is 1, then that means this red circular arc is equal to theta. And this straight side right here is sine of theta. When you make theta very small, you're making this slice of pie really, really, really thin. So you eventually end up getting this kind of thing right here. I'll use the same colors. And this is still sine of theta. And this red side right here is still theta. And you can see, as you keep making this slice of pie smaller and smaller, these two eventually become indistinguishable when these two lines are essentially on top of each other. The straight drop-down segment right here is going to be roughly equal to what that is equal to. So if this is true, then this is true. So there's a simple way to see it, and there's a geometric way to see that the limit indeed goes to 1. Okay, the other special limit involves cosine. If you use a table, for example, you'll see this result very, very quickly. You could also use the result we just saw. Sine over theta is equal to 1. In any case, this one turns out to be 0. Now, one more thing I want to point out about these two special limits, especially the sine one. Let me bring it back. X, theta, these are all the same thing. It's a variable. This is always going to be true as long as these two things are the same. For example, the limit of x goes to 0 of sine of 5x over 5x is still going to be equal to 1. The reason is because as x goes to 0, both of these quantities approach 0 at the same rate. They go to 0 at the same rate. So they are indistinguishable from this basic identity. If they are not the same, then you have to do a little bit of work to make them the same. Okay, for example, if I don't have a 5 down here, but I have a 5x upstairs, then what I need to do is to introduce a 5 in the denominator. If I put a 5 here, I know this will go to a 1. But by adding this 5, I change what I started with. So I have to balance that out by taking away that 5. I put a 5 here because I know this is true. But because I divided by a 5, I got to multiply by a 5 to balance out the change I made. So in the end, we know this guy here goes to 1. That's a 5. 5 doesn't care what x is doing. 5 times 1 is equal to 5. Here's another example using that same technique. Let's do sine of 5x over sine of 3x. This is equivalent to sine of 5x over 1 times 1 over sine of 3x. And it would be great if I have a 5x over here, because I know the limit goes to 1. It would be great if I have a 3x over here, because the limit goes to 1, right? So we'll make it happen. But because I divided by a 5x, I have to multiply a 5x to balance that out. I multiply by a 3x over here, I have to divide it out to preserve the original expression. So this guy goes to 1. This also goes to 1. If sine of 3x over x goes to 1, then the reciprocal of that also goes to 1. The reciprocal of that is also equal to 1. If this is a 1, then reciprocal is clearly a 1. Now, if those things go to 1, these things don't care about x because the x's go away. In the end, we get 5 over 3. And there we go. There's our limit, 5 over 3. That's how you can use that basic limit to make stuff work out. All right, that's it. See you Wednesday. Be sure to check WebAssign for your exam score, okay? X is never 0. So as long as these things can go to 0, they're the same thing. They can be canceled out. This goes to 0. So no, the reciprocal is not 0. Because 0, this can be 0. Only this 0 means that this is a very number that's not 0. This is going to be 0. So a small number and not 0 number. That's how we get it. Sorry. No, back way. So this is going to 0 faster than this. That's how we get it. The reciprocal goes to 0. Because the denominator will be going to 0 slower than the denominator.
Hi, good to see you. I might not be here.
Okay, just the lectures, not the recitation.
I think it will affect the recitations, but I'll give one to my
Okay.
TA as well. Thanks. Up to you if you want to pull your laptop